Thank you very much for the introduction. So let me share my screen. So let me first start by saying a few words about, that this, we have all experienced terrible toll of this pandemic. It has been terrible. Countries like India have certainly not been spared in that, but there's always a good side. And the silver lining, I think, has been that the use by the scientific community and other communities about these tools, internet tools that enable us now to speak. And even though that it was going to happen, but the pandemic has really accelerated the use of webinars. And now it's become normal in a sense to reach out and give a talk which is attended by people from many continents. So I'm really glad to be part of this. I'm very honored to have been invited, especially when I look at the roster of speakers that you have lined up for the summer. It's really amazing. So congratulations for that, and congratulations and all the best for the success of this new Center of Excellence. So let me start with the talk. It's first, and I'd like to say that this talk is also based a lot on contribution from two of my postdocs. First, initially, Yera Akobian, and now Yui Gao is still currently a postdoc in my group. This work has been going on for several years, so I'm going to give you a kind of a very short version of what has been, I think, accomplished during this time. So the topic is, of course, fluid injection. And as you well know, and it has been already said, the introduction of the Center of Excellence, that fluid injection is one of the basic processes used in Earth resource engineering. And whether you think about the geothermal energy when you're going to circulate water in the subsurface, of course, the stimulation of hydraulic fracturing, whether it is conventional or whether it is unconventional, like shale reservoirs, CO2 sequestration, or the disposal of wastewater in the basement, in basement rocks, all of that involve injection of fluid. My particular focus is going to be on water flooding, which is a technique, as many of you know, of secondary recovery for all reservoir. And it really involves injecting at a high rate over many months. It involves injecting water in wells, which are called injectors. And the idea is to push the oil, to sweep the oil towards producers, as you can see from the sketch here. So the idea is that the sweep efficiency is going to be improved if one can induce, during injection, one can induce an hydraulic fracture. You can see that very geometrically, that because then the water is going to flow from a surface, a linear surface, planar surface, rather than flowing from a well. So in weak rocks, and this is one of the applications of water flooding, so very weak reservoirs, which were also very permeable, what is being observed is a very large breakdown pressure. So what is breakdown pressure? Typically, it is the peak pressure that is observed during injection, and it is typically believed that the breakdown pressure characterize the initiation of a fracture. So when inject, the pressure is increasing, and at some stage, the formation is broken, the fracture is going to initiate. And what is being observed and in the field, when in the water flooding, is that the breakdown pressure, this peak pressure, is very large, much larger than expected, especially in view of the fact that those rocks are very weak. And so that's being very counterintuitive, and as I will mention a bit later, that the conventional explanation has been that is plasticity, that as you're injecting, you're causing the formation of plastic zone around the well. So a couple of things, a couple of reminder about the breakdown pressure, as it is traditionally thought of. No, this and the key and the classical, I would say, criterions from the Ames and Ferrers, actually, from the paper from 1967 at the University of Minnesota, where the breakdown pressure is calculated on the basis of the theory of pore elasticity. And it's a simple idea, is that what is the pressure that such that the effective stress, the hoop stress at the borehole wall is equal to the tensile strength. And that is the criteria which is being used. So that's one point, but as I said, it's strictly based on the theory of pore elasticity. But I want to mention also that if you inject fluid in a borehole, then before it breaks down, before you create, you initiate a fracture, then the pressure is going to evolve as a function of time. And the history of this evolution depends on the permeability of the rock. So you can imagine that you have two limiting cases, whether when the rock is impermeable or quasi-impermeable. In that case, the pressure increase is going to be linear because it's only, you are compressing the fluid as you're injecting fluid. You are compressing the fluid, that leading to a linear variation. Or if in the other extreme, where we get a pseudo steady state around the well bore, then you have a logarithm, the pressure evolves as a logarithm of time. And permeability is one of these parameters of geomaterials, which varies over large range of magnitude, typically about 10, as you can see from the graph here, no? Typically about, sorry, going too fast here, about 10 decades, no? Weak rocks would be like with sandstone would be about 1 Darcy, like a sand, and granite and shales could be, even shale could be 10⁻⁹, non-Darcy type. No? So you have this huge range, and therefore, as a function of the permeability, you'd expect various form of pressure evolution as you're injecting fluid. Okay, so the field data are always ambiguous because, I mean, rarely does one do an experiment which is controlled in the field. No? So we have to go back to laboratory. And here I'm just going to show a result of a couple of experiments, a few experiments done in a very weak sandstone. You can see from the data on the, I don't know if you can see my cursor here, but the data, so you have UCS, initial compressive strength, which is less than 1 gigapascal, elastic modulus of 1 gigapascal, permeability of 1 Darcy. So those are highly permeable and very weak sandstone. And to do actually injection test and refracturing test in those blocks is a real challenge, and very few places in the world have the ability to do this type of work. So what you observe, if you can look at the plot here, I've also I'm trying to use. Sorry, I'm trying to use an iPad at the same time, and I think I have a problem here. Just a minute. Unresponsive computer. No, just a minute. Sorry, there's small problems here. Okay, so hopefully that's going to work. Sorry, I apologize for this. So what we see is the result of injection test. So if you follow this dashed blue line, this is the injection rate. You can see that this is what we call step loading. So one increase the injection rate by steps and keep the injection rate constant, in this case for a few minutes. And the response here, you see in black would be the injection pressure, that is the response. And those other lines are the pressure measure at other places in the block. But what you observe, something very interesting, first of all, that instantaneously, as you change the injection rate, you would change the injection pressure, and therefore that if you maintain the injection rate, the flow rate, you don't see an evolution in the pore pressure. So that means that for this permeability and for this size of blocks, what we can see that we are steady state. So there's no time dependency. In a sense, this is kind of summarized in the plot on the right here, where you see the injection pressure as a function of the flow rate. This has been reduced to 2D, so one divide, so because it is in the relation with the model, which are 2D. But anyway, so what you see, and for different experiments, you see that the injection pressure being related to nearly linearly related to the injection rate. And you can see the red line here is the predicted breakdown criteria, the breakdown pressure predicted by the Emerson-Ferrers criterion. And you can see that it is well below the peak. The peak is here. You can see, and at the peak pressure. And so from that point on, actually, you can see also from the plot on the left that as soon as this breakdown pressure, then the pressure drops and everything. The sample is broken in two parts. No? So the question is that what is behind this? Why is the breakdown pressure so much higher than predicted by the Emerson-Ferrers criterion? So again, I have a problem here of for some reason. Let's see. Okay. The question is that what is the cause of this? And then, as I mentioned before, that the idea would be that what explanation have been advanced is the existence of a plastic ring, or maybe is it fracture mechanics? But in that case, we need to invoke a stable fracture propagation if we want to explain the peak pressure. So. Okay, so this is maybe the most important slide of the talk. You know, it kind of summarizes what is the idea behind what I'm going to tell you. Is that the hypothesis here that we are making is that the breakdown has nothing to do with the peak pressure, has nothing to do with the breakdown, the formation, the initiation of a fracture. So the argument that I'm going to develop is the fact that it's a change in the flow regime. And the change of flow regime is due to the fact that we are looking at a porous flow problem, but with a moving boundary, the moving boundary being the crack, which is propagating. And as the crack propagates and elongates, its aperture is changing. We have what is called the cubic law in geomechanics, that the conductivity is proportional to the cube of the fracture opening, and we have a change of the conductivity. So in a sense, it is a flow problem with a moving boundary. And we are going to make the assumption that the linear elastic fracture mechanics is applicable, even though that we are going to assume that the toughness is negligible, it's equal to 0. And the reason behind that is actually CT scan evidence during experiment, which show that the development of a hairline crack, as you can see from the picture below, that does not jibe with the fact that the assumption of a plastic region around the tip, where you would expect a blunt tip and therefore much larger fracture opening. So this is the kind of the motivation behind the proposed hypothesis. And the other point I want to make is that, as I've said before, that doing experimentals very weak material is extremely challenging. And typically, researchers have been using they've been using granular media sand in generally, sand as a proxy for those weak rocks. And you can see on the right here that kind of the map of the fracture pattern that can be generated by injecting fluid, viscous fluid, into a granular assembly. And you can see, depending on the viscosity and injection rate, you see different type of pattern emerging. My belief is that this is this is different from what's happening in weak rocks, because weak rocks have cohesion and cohesion softening. So at the moment that you have softening, you have localization. So as you can see from the figures on the left. So that's the starting point. So we are going to look at models which two classes of model, one for infinite first domain, the other one for finite domain, and see what we can conclude from the modeling. Okay, so at this stage, I want to make a distinction between, try to tell you what is the main difference between conventional hydraulic fracturing conventional reservoir and what we are going to do here. No? And so if you look at the top figure, what we see that we have the way it is modeled, this is kind of a 2D, the so-called KGD fracture. So it's the 2D model, but it's kind of embeds basically what we do conventionally in hydraulic fracturing modeling. You know, so we have an injection point. The borehole is reduced to a point. It's an injection source. You know, fracture is propagating. We have the so-called Carter leakoff, which tells you that the leakoff rate is inversely proportional to the square root of the exposure time. And what is behind the modeling besides elasticity and fracture mechanics is that there's a balance. So the fluid that is being injected is being partitioned between the volume of the fracture and then the volume of fluid that has leaked into the medium, and according to Carter's law. So that is the general framework of modeling. And so let's compare that to the model that we need to develop. First of all, we recognize that in contrast to conventional hydraulic fracture, which lasts, you were inject at most for a few hours. No, here the injection takes place over a period of months or years. So you have to accept the fact that the pore pressure perturbation will take place over a large distance, maybe at the minimum to distance comparable to the fracture length, and that in the simplest mode that the pore pressure is going to be controlled by the diffusion equation that you can see on the top right of the bottom figures. And what you see also that you see the borehole explicitly modeled here. And so that, as you can imagine, that as you are injecting fluid in this water, in this case, in the borehole, first of all, is going to permeate from the borehole, no? And so therefore that we, even before and when the fracture is propagating, so when we do this kind of mass balance, what we have to say that, well, the fluid is not only leaking from the wellbore, that is what is in red here. We have this kind of radial flow. It is also leaking from the crack surface, and you have also some volume of fluid which is stored in the fracture. So an important parameter that I'm going to calculate and is what we call the fluid fraction phi. It's a number between 0 and 1, and that tells you how much of the fluid that is going to the formation is leaking via the fracture surfaces, the fracture wall. So in other words, if phi is 0, that means that all the fluid is leaking from the borehole wall. If phi is equal to 1, all the fluid that is being injected is entering the fracture inlet and is leaking into the medium via the fracture surface. Okay, so that's a parameter that you have to keep in mind. Okay, so major difference between the conventional fracture and the type of fracture that we need to model fractures during water flooding operation. And so I'm going to make the key assumption, and that is what is behind all the modeling that I'm going to report, is that first of all, okay, we are not too ambitious, it's 2D. We neglect the toughness on the basis that it's a very weak material. but we also neglect the storage, the storage. That means the fluid volume stored in the fracture, because imagine that those fractures are going to be very thin, long. We're injecting over a period of months or years, so we can neglect completely the fluid stored in the fracture. Okay. So that's assumption number one. The second one is that on account of the fact that the fracture is that the rock is very permeable. So what we know from the solution from the pore pressure from diffusion equation, we know that we have a region around the wellbore where the solution is steady state, so it satisfies Laplace equation basically, and outside we have actually the full diffusion equation, and the fact that you have what we call the diffusion length, which is increasing as the square, it's growing as the square root of time. So that is the nature of that solution. So we are going to make another key assumption, which is going to make restriction on the parameters, is that the fracture is growing inside the pseudo-steady state region. So that enables us to simplify the problem. Okay, so that's the setting. Even though it has been simplified to, I think, nearly to the minimum, you still have 10 parameters in this problem, so it is not that simple in the sense, but you can do scaling. I'm going to just give you the result of the scaling, and with the scaling you can show that the solution depends, well, the fields, let's say for example the pore pressure, the aperture of the fracture depends on position and time, suitably scaled, and only on two parameters. One of them is the scale borehole radius, the alpha k, and the other one is a pore elastic parameters eta, which is a parameter which characterizes the intensity of the coupling between the pore pressure and the stress. And this parameter is in between 0 and 1/2. I'm going to mention that later on. Okay, so 10 parameters, but we can reduce it to actually two numbers characterizing the problem. So however, it's worthwhile to even simplify further, at least to start, to understand how the nature of the solution, and to say, well, let's put this borehole radius in a relative sense equal to 0, and let's forget about the pore elastic effect. So that means that you have those two parameters set to 0, and that means that there is no parameters left in the problem. So if you look at the bottom equation, you see W is the aperture, P is the pressure, L is the length. So when you scale them, and those are the WK, PK, and LK, you are left with a field, like in this case, for example, for the aperture will be omega psi, which is the position along the fracture, and tau, which is scale time. You only depend on those position and time. So in other words, all those 8 parameters which are left are actually absorbed in the scales. That means that it remains the simplification of the problem. And if you go a bit above here, when you look at the scale, here are two scales. One is the length scale of the problem. You see the viscosity and the permeability and the Young's modulus and the injection rate. But you see also something which is very unusual, is that typically the scales are monomials, are pore law, but you see here in this problem that you have an exponential, and inside the argument of the exponential, you see this I, which is a dimensionless injection rate, which is about of order 1 in water flooding. Gamma is the Euler constant. So you can already see that we have extreme sensitivity because of the exponential. The time scale of the process is very sensitive, extremely sensitive to this injection rate. Okay, so now we can just look at this and try to obtain a solution. So how it is done, actually, I'm very fond of using singular solution. The idea is to take advantage of the fact that the equation governing the solution in the domain, not along the crack, but in the domain, actually linear. And so therefore we can use a singular solution to construct that. And the only non-linearity actually in this problem comes from the fluid flow. So it is this Poiseuille law. It is the fact that the conductivity has a cubic dependence on the crack aperture. So that's the idea, is that to take into account the solution in the outside domain via singular solution, and then to formulate the problem only in terms of quantities which are defined along the crack. And so what are the tools? Well, you look at the fracture as a jump in the displacement. It's the normal displacement. If you have a symmetric fracture as we have, it is the normal displacement jumping across the crack. So we use dislocation dipole or the numerical version of it, which is called displacement discontinuity, and we use to characterize, to account for the leak off, we use source solution. Okay, so so we are going to distribute displacement, dislocation dipole, elastic dislocation dipole, and source solution of the Laplace equation along the crack, and that will be part of the equations that govern the problem. So, and the fact that we are using source solution of the Laplace equation, we can do that because our starting assumption is that the crack is propagating into the region of pseudo-steady state, where basically there is no storage anymore. So so we look at any element of rock, is that what comes into that element of rock, the fluid coming is equal to the fluid coming out. Okay, so I'm not going to dwell on the equation, but this is to give you that's the set of equation. It's not simple because you have the top lubrication. You have this PDE, which is nonlinear because of the cubic dependence on the aperture. And you have an integral equation for its weakly singular integral equation for the post-media flow, and a hypersingular integral equation for the elasticity. Okay, but anyway, this can be solved. Now we can solve that at each time. We can solve for the opening fracture, and gamma, by the way, is the dimensionless leak-off rate, and also the length of the fracture. And once we have calculate those quantities, then we can extract from that the fluid fraction, this amount, how much of the fluid being injected is going into the fracture and leaking into the medium from the fracture surface. We can calculate using the expression at the bottom. So, but it is a secondary, variable. Okay, so when you analyze that solution, so remember that we have only one. This only depends on the position, on the scale position along the fracture, and on the scale time. So what you see that, as is typical in this class of problems, we evolve between two asymptotic solutions, the small time asymptotics and the large time asymptotics. And the small time, what we have is that phi equals 0. So what that means? It means that all the fluid is leaking from the wellbore, even though the crack is there, it is hydraulically invisible. It does not change the pattern of flow. And you can see that from the pore pressure field on the bottom left here, which you see the level set are circles. Now you have radial flow. And on the right, what you see, it is the other extreme. It is the late time solution. So now the wellbore is invisible. By the way, those two pictures are made in such a way that we scale. We look at the fracture always on the same. The fracture occupies the same length, so therefore that. So the scaling factor, of course, is different. But in this case, we don't see any radial flow anymore. We see this kind of elliptical or linear flows, as it's sometimes called, pattern in the pore pressure. And so in that case, we have, in a sense, we can see that the injection point is invisible. We don't see the radial flow, and we have unstable crack. What do I mean by that? Is that you can see from on the plot here, where you see the injection pressure as a function of time, and you can see that in the small time asymptotics, no, you have this basically the reservoir flow is a trivial solution of the diffusion equation, where you observe a logarithmic increase in time of the injection pressure, and then you have a peak, and then you have the late time asymptotics, where the injection pressure decreases as a part of time, but -1/4. Okay, so you see that already here that this peak pressure is really corresponding to a change in the flow regime. And we can go further on that. We can actually look at the solution. So as it is well known, those asymptotic solution actually time similarity solution. So what does that mean? That solution of space and time becomes typically a time to a certain power times a function of space. No, as you can see in the box, the red box and the blue box at the bottom, and you see a difference dependence on time, whether you are in the early time or in the late time. So, for example, if you look at the opening at the inlet, no, at the wellbore, initially at small time you observe a square root dependence on time of the opening, but at late time you observe dependence of time with a power of 1/4. Okay. All right, and you see very different. Red is early time, blue is late time. You can see very different pattern, and particularly you can see for the injection pressure, you observe this kind of a logarithmic singularity that's the hallmark of the small time asymptotics. Okay. So a particularity of this solution is that you can prove that not only at the small and large time, but also at any time, this particular problem is characterized by a fracture length which is increasing as a square root of time. So what does that mean? It means that not only the diffusion length, that means this kind of interface which separates the pseudo-steady state from the diffusion equation, is increasing also as a square root of time. That means that if the fracture initially is contained within that pseudo-steady state region, it will remain contained at all time. Okay. Now, so the model gives you some idea about what is happening. In particular, kind of support this hypothesis that the peak pressure is actually a change, an expression of the change of regime, but we need to enhance that, and we need to incorporate, of course, two things. The one is the borehole. This it's alpha k, and again, it's in a dimensionless form because it's radius divided by this length scale of the problem, but also pore elasticity. Based on Biot theory of pore elasticity, and this coefficient alpha there, no, it's not the same as the alpha k, but the coefficient alpha you can see from the equation for epsilon here, which is simply, if you put alpha equal to 0, it means simply that the volumetric strain is proportional to the mean stress, and k is the bulk modulus. But if you have pore pressure in the material, then you have counteraction due to pore pressure, and that is measured. The intensity of that is measured by the coefficient alpha, the Biot coefficient alpha, which is between 0 and 1. Okay, so the key parameters is actually eta, which is a combination of this Biot parameter and the Poisson ratio. But you can, as I said before, you can prove that it is in between 0 and 1/2. Okay, so now the solution is of course a bit more complicated because it has parameters, no, besides the variable space and time, but it has only two, despite the fact that you are starting with 10 physical parameters to start with. Now you have the scale borehole radius and pore elasticity coefficient. So the tools, the methodology that we have used for the simplified bare bone model is the same. It's a bit more complex, but it is the same idea. We rely again on using a singular solution to characterize the displacement discontinuity, but also to characterize the flux discontinuity. The source solution, the fluid source solution takes into account the pore elasticity, and the dislocation solution, and both of them have images inside the wellbore. You can see that the wellbore in the dashed blue line, and those solutions are due to for the elasticity solution is due to Dunn-Durst and Murat. So it is, so in a sense, what I want to say is that the singular solution implicitly take into account the existence of the hole. So we don't have to model explicitly the borehole. Okay, so that is what is behind. But besides these important details, no, the methodology is the same. We can reduce all the equation to in terms of variables defined only along the crack, and then when we manipulate and we discretize at the end, we can formulate the problem either in terms of, for example, only in terms of the opening. So it leads to the formulation of a nonlinear system of equation in terms of either of the opening or in terms of the flux discontinuity. Both methods are possible. Okay, so so that means that let's look at the solution here. And here is what I call a phase diagram. So in terms of two quantities, which are solution of the problem, one is phi, it is this fluid fraction, and the other one is lambda. It is it's a measure of the length of the fraction. You can see that from the top equation, that is actually the length divided by the square root of time. And in the previous model, it was set equal to 1. So that means that when it's equal to 1, it means that the fraction grows like the square root of time. So in terms of the previous model, what we have, our space of parametric space was one-dimensional because it was only phi. Remember that now, as you go as time is increasing, phi evolves from 0 to 1. So in a sense, we are looking, if you can think of that as a phase diagram, we are looking at evolution along what we call the crack, the KHD crack edge. Now it was moving from this vertex, we call that the vertex I, which is what is this rock flow solution that I mentioned before to vertex F. Now we have, it's a bit more complicated now because we need to take into account the fact that we have the existence of explicit existence of the borehole. That means that initially, as the fracture starts to propagate and the fracture length remains small, or maybe of the same order as the borehole radius, then the fracture is not evolving as fast as the square root of time. So, and that is reflected by the fact that this parameter lambda, well, initially is less than 1. So imagine that as time is evolving, you have a certain set of parameters. So you have an alpha k and an eta, and here the dash one corresponds to the maximum value of eta. The continuous line means is 0, so there is no elastic effect. No, but take for example this the yellow dashed line. So as time is evolving, the solution is evolving that space along this yellow dashed line. And you can see that initially it is along this edge here where phi equal to 0. That means that the fracture propagates from the wellbore, but the flow remains radial. It means that the fracture is still invisible. And as soon as the solution is departing from that radial flow edge, then you start to see the effect of the fracture. The fracture is perturbing the flow pattern, and when it reaches what the black dashed line, it means that means that the peak pressure is reached. No, so the time is implicit in these parameters. Just imagine that the time is evolving as we are moving from one to the other, and what we see that as the the borehole radius becomes smaller and smaller, no, in a relative sense, then what we see that the solution evolves along two edges, one along this radial flow edge, then it reached this, what we call this intermediate, it's an intermediate time asymptotics, which correspond to the rock flow that I discussed before, and then it's following this KHD crack edge. So you have two, and you can see also from that that you have two time scale, one time scale to go vertically and one time scale to go horizontally. So actually the problem is characterized by two time scales. So this alpha k in a sense is a ratio, it's a measure of the ratio of two time scales. Okay, and so that is the solution here in the. So let's pick up maybe two of them. Let's look at the injection pressure pi W versus time. Those are log. So first of all, you have this radial flow, the injection pressure evolving as the logarithm of time, and then it reaches kind of a peak, and then it's following this kind of a large time asymptotics. And really what you can see from this plot is that depending of the size of the borehole, no, you have 10 here, you have 3 values, then the solution is being delayed in time, okay? And yeah, we can see that also from the lambda, similar thing. So initially, fracture is growing less than square root of time to reach its asymptotic value of 1, where it is proportional to the square root of time. Okay, similar thing for the fluid fraction. You see this evolution, and in particular the aperture here shows that it shows actually two regions, I mean, of radial flow. First of all, initially it's completely dominated by the well bore. Then it is dominated by this this rock flow. So that means that when we are on this branch here, when the aperture behaves as a square root of time, it means that the borehole is very small. Is not visible in a sense, no, from a mechanic point of view, but also the fracture is hydraulically invisible. Okay. Let me switch. Maybe mention just. Set maybe just a set of possible field data. Those are a set of parameters which are plausible. And what you come, if you look at the red box here, what you see that from in terms of physical quantities, well, we see that first of all the peak time is reached after more than 1 month, 1 month and a half, no? And the peak pressure is very large. No, you look at the peak pressure of 44 megapascal. Compared to a stress, if you look on the left, a far field stress, which is about 36 megapascal. So it's 8 megapascal above the minimum stress. So it is very large, the very large net pressure that's consistent with the observation. Okay. And the extreme sensitivity of the time scale, so the time it takes to go from one solution to the other solution, from this radial flow to this kind of elliptical flow, this measure is, as I said before, is very sensitive to the injection rate. And it means that if the injection rate is smaller than 1, approximately smaller than 1, then it becomes unobservable. So what does that mean? It means that, practically speaking, means that you have always radial flow, okay? And you will never observe, no, let's say, for example, I is equal 1/2, you will never observe a peak. You will always observe a linear, a logarithmic increase of the injection pressure. Okay, maybe I will, yes, I will take only maybe a few minutes to mention, to see, okay, what we can do for as a model for the lab experiment. No, besides the fact that in the lab, of course, it's finite, the domain is finite. We don't have infinite domain as in the previous case, but the key difference, the fact that now in the lab the solution is time independent, so it is always steady state because of the high permeability and the low viscosity of the fluid, high permeability of the rock. So So before, the stability of the crack, in the sense the boundary between stable and unstable, which correspond to the peak pressure, that was corresponding to a certain critical time. No, so if the time was less than the critical time, that the pressure was always increasing. Above that critical time, the pressure is decreasing, so we can interpret as being unstable, quote unquote. No, and but in the lab, of course, we don't have that. No, and the stability is in terms of the critical injection rate. So if the injection rate is smaller than this critical value, it is stable. That means the pressure will keep increasing as you increase the injection rate, and unstable otherwise. Okay, and so again, it's the same type of methodology is being used. No, it's a bit more detailed because, of course, we have finite boundaries. So we have also to distribute singularities along the finite boundaries to take into account the boundary condition applied on the finite boundary of the domain. But it follows the same idea. At the end, what matters is that we have equation in terms of a quantity defined only along the crack. And the sketch that you can see here shows that you can also take into account the double symmetry of the problem. So the idea is to reduce the size of the nonlinear system of equation that you have to solve in order to obtain the solution. Okay, and again, it's a combination of boundary element method and finite volume method to discretize the Poisson equation. Okay, and so you can see here lambda again is this length. No, so if it's equal to 1, it's equal to 1. That means that the crack has reached the outer boundary of the sample, and you can see for different value of lambda, so which correspond to this one-to-one relationship between the crack length and the injection rate, and you can see change in the flow pattern from radial to this kind of elliptical flow. And if you can see, if you can look at the plot on the movie on the right, I hope that the internet is fast enough so that you can see that. So you see, and it's not an evolution, so don't think that as time. It's simply how the solution is changing as you are increasing the injection rate. And you can see that initially you have this linear flow, and then at the bottom image, you see the peak pressure, which is, again, it is the same idea. It's marking a transition between the two flow regime. Okay, and then we can solve that. So we can look at that. For example, if you look at you can solve that for several different value of the parameters. You have a few more parameters in this problem because due to the finiteness. But in particular, let's look at this H, which is a certain scale version of the applied stress, which is the stress perpendicular to the fracture. S is a measure of the deviatoric, and we can also solve for the toughness. But turns out that the toughness in the previous model we set to equal to 0. Because it's finite, we took that into account, but we can show that actually it has an extremely, for plausible value of the toughness, this dimension toughness can be treated as being 0, negligible again. Okay, and you can see, for example, on the top left figures, this kind of a one-to-one relationship between the crack length here and the injection rate, and then the other plots will show you, for example, the top right will show you the fluid fraction is changing the crack length, or you can translate that into how the fluid fraction is changing with the injection rate. Okay, same story in terms of in terms of the injection pressure. You can see here on the bottom two plot the pressure, injection pressure versus either the injection rate or the crack length, and you see a peak again marking the difference between the transition between those two flow regimes. Okay. Okay, so let me pass that, and maybe that I'm close to the conclusion. Here is a comparison of the experiment. It has to be taken with a bit of grain of salt because the experiment is 3D, so we have to make some assumption, or has to transform the measurement, the 3D measurement, into a 2D. But we can do that. And what you can see in the bottom left figure, you see the injection pressure now in megapascal as a function of this reduced injection rate. You see the data, we see the prediction, no honest prediction in the sense besides this translation from 3D to 2D, all the other parameters have been in a sense measured or given to us. So we have not played with those physical parameters. And you can see here, well, we match. We have a good match for when eta is at this maximum value. It may be a bit serendipity, but at least what we show that with this model that it supports what I want to say. It really supports this hypothesis, and that we have made, that it's actually a flow problem. The peak pressure is an indication of a change in the flow regime. And again, we have this very large predicted value of the peak pressure, which is about at more than 50% larger than the breakdown pressure. So the breakdown pressure is somewhere here, and then as we're increasing the injection rate, the fracture is propagating in a stable manner. So that means that if you keep the injection rate below the critical value, the fracture will not propagate. But at one stage, when you reach the peak, then the hell breaks loose, and then the crack becomes unstable. And that's what you observe in the experiment. Once you reach a peak, the fracture reached the end, the boundary of the experiment immediately. Okay, so that is the concluding the talk. I hope that I've been able to convince you a little bit that in those formation, very weak formation, we should think of the problem as a flow problem with a moving boundary. And that the peak pressure, now we have this, even though the model remains still simple, but that we can see at least convincingly that we have a transition between two flow patterns. As I said, that we have one of the puzzling thing, which means that in terms of robustness of the model, because in terms of the field operation, we never know exactly what are the parameters. It means that we have an extreme sensitivity of the time to a this-dimensional injection rate, and that means that maybe explain why it is so difficult in the field to predict. And so therefore it has to be done on in a sense. This is an explanation of, but it cannot be used as prediction. It is maybe to provide some understanding of the process and what can be done in a sense to reduce, for example, the time scale. And so that means that, for example, pore plugging by impurities, those water is filtered, but still it has impurities. If you have impurities, then you are plugging the pore of the fracture and also of the wellbore. That actually you can show that introduction of the time scale. So you can, this also the possibility of manipulating that. So for example, if you imagine that you are pore plugging, that means that you are going to increase the speed, the growth rate of the fraction. You can maybe take advantage of that. Thank you for your attention, and I'll be pleased to, if there are any questions, I'll be pleased to answer them. So maybe I'll stop sharing. I can see some.
Thank you very much, Professor Detournay, for a very insightful talk. We have a few questions. I think I will ask the person to unmute themselves, introduce themselves, and ask the questions to you directly. So the first question we have is from Dakshina Valiveti. Dakshina, can you hear us?
Yes, 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 I can. Am I audible?
Yes.
Great, thank you. Professor Detournay, this is Dakshina from ExxonMobil. Thank you for the very insightful presentation. This is very interesting. Couple of curious questions. In the mathematical model itself and the ensuing calculations, what are the differences between a finite boundary and the infinite boundary? How do you see that manifesting in the solution?
Yeah, so the infinite boundaries are as time. So we have so the solution, in a sense, the formulation of the problem assumes that the fracture is growing inside this pseudo steady state region. And so therefore that enables us, as I mentioned, that enables to make some simplification. For example, the source solution that we are distributing along the crack, actually steady state solution, because the perturbation we assume is consistent with the Laplace equation, but you still have time. So what does that mean? It means that as the diffusion length is increasing, as square root of time, that means that the background pressure is increasing. And so that is why it is dependent on time in the solution. While in the finite domain, well, it is steady state. And as you can see from the experiment, we can see that there's no time dependence. As soon as you change the injection rate, you are changing the pressure, and the pressure is not evolving.
Right.
So that is the key difference.
Okay. And then when you're comparing with the experiments, how do you see the heterogeneity manifesting in the solution, which is not a component of the mathematical model, right?
Yeah. So something which is quite amazing. So in a sense, it's a flow. As I try to stress, it's a flow problem. It's a peculiar flow problem, and diffusion Laplace equation. And something that has to be said, I mean, diffusion equation is extremely robust. It's amazing. I mean, you're working for ExxonMobil, so know that more than I do. That, I mean, it's amazing the prediction that you can do with the diffusion equation. That it somehow it forgets about small scale heterogeneities. It does some averaging, and therefore it works extremely well. For example, I know some faculty here are interested in seismicity. We know, for example, that the seismicity is controlled by the diffusion when you injection. So we know that the region of seismicity, for example, is growing like square root of time. Again, completely consistent with diffusion equation. So it is very obvious. So I think the small scale heterogeneity, I don't think plays a big role.
Thank you. Yeah, I think I'll fall back with just one final note. I think it'll be interesting if we can have the influence of perforations. In addition to the wellbore. I know that's already pushing it, but I think that'll be very, very, very relevant and practical for us.
I think it's a very interesting question, and I will tell you what I think. I don't think it matters.
Okay.
Because our bare bone model does not have the borehole, but still, we do something very strange. To solve the problem, I didn't go into the details, but in order to solve the fluid entering the fracture is actually entering via a negative sink, and despite that, it's kind of wiped out. So I think that what's happening, even if you have perforation in the early time, you're still going to be at small distance, from the wellbore, from the casing, you're still going to have radial flow. So yes, you have an extra resistance to flow that will be very easy to account for with some kind of a cake or some kind of resistance to flow, but you still have radial flow. So it actually doesn't matter. So those things are very forgiving, I mean, that's the beauty of diffusion equation.
Yeah. Thank you. Yeah, I'll let the others also have an opportunity of questions. Thank you very much.
Yeah, thanks, Dakshina. So the next question we have is from Professor Tejas Murthy. Professor Tejas, if you could unmute yourself and introduce yourself and ask your question.
Yeah, thank you. Hi, Professor Detournay. Nice. Thanks for a very nice talk. I had two questions to ask you. One is, perhaps I missed this when you were presenting, but where did you fold in the fluid properties in your dimensionless parameters? Because I don't know where the fluid properties were getting folded into the equation.
Yeah. So okay, so I didn't show all the detail of the scaling. I only showed two scales, no?
Right.
For the length and one for the aperture, and so those scales, no, for example, the pressure scale depends on the viscosity, depends on the permeability of the rock, and the viscosity. So actually there are one parameter which is only property of the fluid, which is the viscosity.
Right.
And I should have said, no, I didn't mention that because I'm not that I didn't want to hide, but simply because of time, that the fluids that we're injecting, we assume that has the same viscosity as the indigenous, as a pore fluid. No, it's a small approximation.
Okay. Sure.
But the diffusivity is of course a function of the viscosity. No, so that and the kappa, which is the mobility, is also a function of the viscosity. So it's embedded in the scales.
Okay. I guess then this is also somewhat a related question. For the limiting case where your phi was equal to 0, can you comment on the deformation of the material itself? Yes. Of the solid.
Yeah. Of the solid. Yeah. So it's a crack. Then it becomes only a crack. So in a sense, you can forget. Maybe let me try to go back. Sorry, let me go back here to maybe one plot here I can show. So if for example, let's take, so that pertains to the finite domain, by the way.
Yeah.
And so what you see here, I didn't show this slide, but you see the fluid pressure as a function of position. So the crack now occupies, let's say, 1/3 of the block, no? And you see that positive value and negative value, because I mean, this crack is in limit equilibrium. It has zero toughness, so you have to have negative net pressure. You see the opening profile, so it is very different from the Griffith crack, no? Mm-hmm. As you can see from the profile. And what you see also, by the way, is again something that I didn't stress, no, but is the leak-off rate. So it is very different from the leak-off rate that people are using conventional fracture, because the leak-off is, as I said, the famous Carter leak-off is inversely proportional to the square root of the exposure time, which leads to a singularity of the leak-off at the tip of the fracture. But you see here that it's a very regular function. Actually, it's a power law with a power law of 7.5. And that has to do because in the background is Laplace equation. Laplace equation does not tolerate singularities, and that is smoothing the field. So it's a crack. It's a crack with that which has this particular leak-off function. And you can forget at that stage. You can see the pressure is finite. It has lost the singularity, the log singularity that it had in the early time. And if I have answered your question.
I'm sorry. At the other case where phi is equal to 1, where you have fluid flow through the crack itself.
Yeah. Sorry.
Sorry. Go ahead. I didn't mean to interrupt you. So I couldn't understand what was the deformation of the material. I mean, I get your point here, but so there seems to be no clear distinction between the deformation of the solid when you have phi equal to 0 versus phi equal to 1, right? Am I missing something?
Yes, I mean the deformation is different. So if you have phi equals 0, that means that you have radial flow. So
Right.
you have a radial pattern of deformation, like classical pore-elasticity solution. If you look at the infinite domain, and in this case, when I look at crack length equals 0.91, basically phi is nearly equal to 1. No, so now you have a crack. You have a crack you have a crack in a medium, whether infinite or finite, no? And it's, and it has a very different profile. The crack, so in terms of the crack opening, it's very different from Griffith flow because of the pressure loading. And then the deformation in the solid, no? We didn't compute it, but I mean, it can easily be computed once you know the crack opening. You can calculate the deformation.
Sorry, I don't mean to hold on to this question a lot longer, but so one is essentially, does that resemble a cavity expansion solution is what I was thinking of?
No.
Okay.
No, that's it's still an elastic. So I mean, if you go very far, no, if you look at the infinite domain, no, if you go very far, if you look at large distance compared to the crack length, then what you see, of course, it's a volume increase, no, because you have in 2D you have the displacement as 1/r. But if you come a bit closer, what you see the singular behavior. You see a dislocation dipole. Okay. That's what you see in the far field. But this is remember that the background is elasticity or pore-elasticity. So that's very different from what if you are thinking more in terms of like treating the problem from a plasticity point of view. For example, if you are looking at experiments which are done in injecting fluid in granular media, that's a different story. And then that would be a cavity expansion model.
Okay.
But this is the background here is elasticity, not plasticity.
Right.
I mean, cavity expansion model, of course, it's a mix. Huh? It's plasticity and
sure.
Yeah.
Yeah. Is it okay if I ask one more question?
Sure, Tejas. The last one.
Yeah, sure. Okay. Yeah. I mean, I was just thinking hypothetically, if let's say you had sort of reversed your experiment in the sense you had a cylinder of rock with the fluid surrounding it, and a sort of a notch that was trying to inject the fluid into this schematic. Then, I mean, I know the boundary conditions would be slightly different in the problem, but I was just wondering if you had sort of this confining pressure around a single solid piece of rock, wouldn't you have a slightly easier control of the pore pressure and at least the confining pressure and the injection pressure? That would also be much easier to measure, and then the propagation of the crack would essentially be a little more easy to handle or visualize. Can you just comment about that?
It's an interesting proposition. I think the first thing to wonder is that is how the everything, of course, dictated by the pressure profile initially. So when you go from outside to inside, it's of course different from inside to outside. But I cannot really comment on that. I think first of all, the experiment where we were not responsible for the experiment; those were done in commissioned by oil company and it's a commercial lab. So we had only access to the data, we could not participate in the design of the experiment, which would lead to very different probably way of doing things, because then we would use a mathematical model to do a proper design of the experiment. But that being said, I think that it was reasonably well controlled in terms of the certain injection rate and the confining stress and the pore pressure. There was a bit of problem with the pore pressure boundary condition because of such a high flux, but we in a sense, we were able to correct that because at the outlet the pressure was measured, so we could do that. So yeah, I don't know. It's not a satisfactory answer, probably most likely to your question, but yeah, that's what I can say at least.
Thank you very much once again for this wonderful talk.
Yeah, thank you, Tejas. Sorry, didn't mean to cut you off. It's just in the interest of time and other questions. Thanks a lot. The next question we have is from Abhijit. Abhijit, if you could please introduce yourself and ask your question to directly to Professor Detournay himself.
Thank you, Chandra. Yeah, Professor Detournay, it is a wonderful presentation talk. I mean, you have shown, you have developed an elegant, I would say, semi-analytical approach to understand some of the intuition we have, like lick off, I mean, based on injection pressure and mechanical properties of maybe the rock, something like that. And I have a couple of questions, like, is it possible to get a lower limit of the permeability of the formation when the hydraulic fracture will not occur in terms of mechanical properties or yield stress of the rock?
Yes, I mean, that's an excellent question. So in a sense, everything is contained in, I mean, the key parameters is this injection, dimensionless injection rate, no? Which is inversely proportional to kappa. So in other words, if for example the permeability is increasing, no, that means that the dimensionless injection rate is decreasing, and what's happening then is that the time scale is increasing exponentially.
Okay.
So that the direct response to your question is that yes, it will happen. It will always happen, but because of the exponential, it might take the time of the universe.
Okay.
So it's extreme sensitivity because of the exponential, and so that's what I think that no predictions are impossible.
Okay.
You can only use this as understanding, no, and do field experiment to try to see where we are, no. So it is a guide it's a guide to thinking, but yeah, it's a very good point. Thank
you so much. And I have a few more questions, and like, I mean, one simple thing, like, will the results will depend on the far field boundary conditions?
So I didn't get the question. I'm sorry.
Will the results or the analysis depends on the far field boundary conditions, let's say displacement 0 or stress-free boundary conditions anyway?
Yeah. So so in the infinite domain, that is naturally taken into account, because we are using to singular solution of elasticity and Laplace equation. So we have the correct infinite boundary condition.
Infinite boundary condition, but it's
maybe
possible.
Naturally.
Maybe. Yeah. I think the effect of the pore pressure, because pore pressure increase sometimes causes expansion of the rock. If there's a free stress-free, then the rock will expand. Of course, the expansion rate will depend on the pore pressure diffusivity, and maybe the pore pressure diffusivity and the time scale of the pore pressure, I mean the length scale or time scale of the pore pressure diffusivity and other time scale of other phenomena, relative difference may be important to consider, but
yeah. So I mean, we approximate the problem. It's a linear problem, except for this flow inside the crack, which is this very strong non-linearity. But everything else is linear. And if, for example, we're in the finite domain, we could change the boundary conditions. That is not that's not the problem. But I think the boundary conditions that we are using are was reflecting the laboratory experiment. So in laboratory, it's a vessel, you are using so-called flat jack, and you control the flat jack so that as to impose the non-stress. They made attempt to control the pore pressure at the boundary, at the outside boundary. But as I said before, that because the ejection rate was so large, and because you have some resistance to flow outside the apparatus, actually when you are as you're increasing the ejection rate, there are difficulty keeping up the pore pressure to the same value. But it was measured, and therefore, in a sense, it doesn't matter for us. No, we can just account for that as long as we have the measurement. We can. It was extremely hard experiment to do.
Exactly. Yeah. I don't know, the numerical simulation can give any light on this? I mean, what do you think? Nowadays, like a phase fields based method or something like that available nowadays. What is your? You mean
are the simulation able to shed light on the nature of the boundary conditions?
Yeah,
of course.
Yeah. So okay.
Yeah. That's the. Yeah, that's and I hope that's.
Yeah. So I mean, we are recently also developing a code on using phase field method. Okay. So So just few months before we started working, we are validating it. So maybe we can try that. if we get any answer to that question, maybe I'll inform you if I get anything on that.
I'll be delighted if you want some reference solution. I'd be delighted to share that with you. I mean, our model, as you can see, has a lot of restriction on the so it's, as I said before, it's more thought to think and also, I mean, the other thing is that, and I've been involved with a lot of people on developing reference solution for hydraulic fracturing. They're all very simple in a sense, very simple setting. And I've always argued that there are two benefits to them. The first one is that it tells you at least you can do scaling. That you can, it's more difficult when you do numerics, although you can still do it. But I mean, at least you can have, it's easier to have an insight on the scaling when you formulate the problem as we've done. And the scaling for me is the most important thing. If you know the scale, that means that you have a very good control of the problem.
Yes, absolutely. Yes.
And the second reason that I think that there's some value, I'm trying to sell what we have done, this bit of value to what we have done, is that numerics, it's a very hard problem numerically. And any time that you have a moving boundary, and especially the very peculiar boundary condition at the tip of the fracture, and you can see here is very different, then you need reference solution just to have some confidence in your code. So if that is the weighted solution I use, I think that we have accomplished something useful, because we provide reference for numerics, which at the end we have to do, because we can put more physics into the modeling.
And if two more questions, maybe I'll ask now. I mean, can I call your approach as a reduced order model? Is it correct to say? Or I mean, I saw the equations, but not very sure.
It's not reduced in the sense of, for example, if you do structural analysis where you are lumping, for example, and it's not in that sense. It's a reduction, but you're right. It's a reduction in the sense that we're trying to take full advantage. I mean, the problem, as part of it is linear and part of it is non-linear. So we take advantage of the linearity just to simplify it. So we don't have to solve. We don't have to solve in the domain. You can solve only on the crack, which is tremendous. You can probably guess that and by the way, I need to acknowledge the contribution of my postdoc Yui Gao, particular, who has been the guru behind the development of the code. Everything has been done in Mathematica.
Okay, right. Okay.
It's fairly fast because
very fast. Mathematica is very fast. I have seen it. Yeah. And just okay. So your crack was growing in length, right? What time?
Yes.
So
yes.
I believe that you consider the stress concentration at the tip.
Sorry, at the tip.
No, I mean crack propagation. I mean that means I hope that your model. I mean I didn't understand. Probably I missed it. So at the tip of the crack, there's a stress concentration.
Yeah. So we. Yeah, we did. I didn't dwell on that again.
Okay.
Apologies for that. Yeah, we're using propagation criterion. So what I've presented is we assume, and you can show that it's a relevant assumption that the toughness is negligible. So we put toughness equal to 0.
Okay.
In that, but it's if one look at the if one look at, maybe I can just flash it. So
okay.
Then there is no ambiguity here. So that is for the reduced model, but I mean, so the fracture propagation is here on the, which is basically the weight function, the Rice-Buchner weight function.
Okay, I see.
But I mean, you can put K1 and it makes things more complicated. The beautiful thing here is when you put equal to 0, and you neglect the borehole radius and the pore elasticity, then strictly, which is still amazes me, it's a beauty of the mathematics that the crack length increases as square root of time. It's just absolutely amazing, irrespective of the flow regime. No, it is a mystery of nature that I mean, but that's what the math tells you.
Yeah. So
Okay, thank you, Abhijit. I think we'll just give opportunities to someone else.
Thank you so much. Okay, thank you.
My pleasure.
Justin, can you introduce yourself and ask your question?
Yep. Hey, thanks, guys. Thank you for the talk. So my name is Justin. I'm a geothermal reservoir engineer and a researcher at VITO, the Flemish Institute of Technological Research in Belgium. And so, sorry?
A compatriot.
That's right. I'm a recent import, though. So Chandra and I go back from grad school, and I've been in New Zealand as a reservoir engineer for a decade. So anyway, we have we're working in carbonates, deep carbonates, so they're kind of strong, low permeability rocks. But we have a hypothesis going at the moment that we're changing flow regime as we're injecting. We're seeing it in our injection fall-off tests from like a matrix flow to a fracture flow. And I'm wondering what to look out for if we go, kind of to Abhijit's question too about numerical approaches. We've been kind of coming at that hypothesis numerically, but it's an open-ended problem and it's not a unique solution, right? And so I'm wondering if I can apply something like this to kind of show that. And so I'm wondering a couple questions, I guess. One is, have you looked at, what are the things to look out for with this approach in kind of stronger, low permeability rock? If you've looked at anything like a carbonate.
Yeah. No, so this limitation on this approach and the key limitation, because I mean, we were looking at water flooding of weak rocks, no? The key limitation is the fact that we assume that this fracture propagates in this pseudo steady state region. This is not going to happen in your case. Yeah. So we need, what does it mean? It means that we have to be a bit more, we need to relax. If I think in terms of the model that I have been discussing, we need to relax this hypothesis. And therefore, the source solution that we have to distribute mathematically would be the source solution of the diffusion equation, not from the Laplace equation. Okay, so that's on the math point of view. So it's a much tougher problem. I mean, even analytically. So I would probably go like you. I would probably go numerically because of the diffusion equation. Yeah. The thing to watch, the key parameter is the signature. How the injection pressure is changing. That is the key thing, because as you are changing, as this crack is growing, it's changing the flow pattern, and we know that from all the reservoir engineering that now the dependence of injection pressure on time is going to change. You know, so that is the. I mean, the first thing to do is, I mean, if you have access to field data, is to do this type of analysis, no, and you see that in the field data, and then go back to the numerics. But numerics should show that, no?
Yeah, no, that's what we're seeing is we're seeing like an increase in type of channelization. So perhaps, so we're seeing permeability go up, but some sort of fractal dimension, like you know, we're going from a matrix flow to a fracture flow as permeability is going up. So we're, you know, the flow is becoming less dispersed, but more channeled as as pressure goes up. Yeah.
Very interesting. But in your case, the big difference with what I've shown is that because of the lower permeability, you have longer fracture. Okay, you have toughness, but you have longer fracture then.
Yeah.
So yeah,
we're not sure we're actually propagating a fracture, or that it's just an existing fracture that we're managing to open up, right? Yeah.
That's another story, of course. Yeah. That's complexity of the natural world.
Yeah. No, thanks for that. It was very interesting.
Thanks.
Thanks, Justin. So we have a few questions here in the Q&A panel as well. So Mr. Subramaniam is asking if we could use more viscous liquid instead of water to create the fracture in weak rocks or porous rocks.
It's an excellent point, indeed. No, if somehow that what you want to do is actually create the fracture, and to do that you need to have a more viscous fluid, and somehow hoping and so that is little damage, no, to the permeability. So maybe you have to use particular type of chemicals. That is not my field, but switching that, and actually that's the company. So when we were doing this work for initial work for this company, that's the kind of thinking they were doing, because initially the thought, and that's kind of interesting point actually. The thought was toughness. No, that was the reaction of hydraulic fracturing engineers. No, everything's toughness. So you see large injection pressure, therefore you have large toughness. No, but if you have a large toughness, you cannot do anything. That is life. No, you have to deal with it. But if it becomes a flow problem, then you can be smart. You can start to engineer, and that is your suggestion. That, no, in the sense that switching the fluid, no, would do something like that. Propagate the fracture and then switch to water, some kind of
Okay, so last question, and then we'll let you go. I think we've held you enough for a lot of time here. This is by Jitin, and he's asking, how do we treat moving boundary conditions in numerical analysis of the model?
Yeah, this is, I think that a lot of people, I think, probably attending this talk, who are more qualified than I am on that able to respond. There are different methods, no? I mean, I heard phase field method, no, which is one of the popular technique nowadays to do that. I've more on the type of people who have been using, because I try to limit myself to simpler problem, to use dislocation solution. So in that sense, it's fairly easy. So we in a sense, we are adding elements, no. So but method, you have XFM also method, which are people have been developing XFM method for hydraulic fracturing, say, and that is quite a field, because one of the difficulty for those of you who are involved in numerical modeling of hydraulic fracturing is the change of singularity. We don't have, in general, in particular case, yes, but we don't always have the linear elastic fraction mechanics singularity, the square root of x, square root of the distance. We have actually a whole world of singularities, and that is the work I've done with colleagues and students now to try to map the nature of the singular tip, as a function of the parameters, for example, the velocity of the fracture, the leak of the viscosity. So that has to be done if you want to develop numerical methods which are robust and do not require too many elements, because we all know that in computation mechanics, if you know the correct singularity, then you can be smart and you can use very rough coarse mesh. Yeah, but I think other people might be more qualified than I am on that question.
Thank you, Professor Detournay, for giving an excellent talk and also patiently answering so many questions. As you can see from the number of questions you received, there was really quite a bit of interest. It was indeed a pleasure hosting you. And if there are no further questions from anyone else.
Yeah, just a second. Emmanuel, thank you very much for presentation. It's excellent as always. So already the problem is nonlinear coupled and it's having its own complexities. So when are you planning to add one more complexity on plastic deformation? That's my question.
I would love to do that. Somebody has to fund me.
Sure.
And the complexities are, I mean, they're very important. The first one is, and in a sense, we know what to do. The first one is including impurities.
Yeah.
People who are involved in water flooding, for example, they know that. They know that impurities, pore plugging, is a key. And the beautiful thing that the problem, as the more complex problem that I present, is characterized by 2 time scale. We add only 1 time scale. And it's also possible to introduce the finite thickness of the reservoir using those extended PKN, which are actually quite robust model, not PKN, but clever PKN, which take into account the coupling elasticity, which introduces the time scale. So you can see that there's this way to do it. But again, it requires 2 things actually. Of course, financial resource is one of them, but it requires very qualified student, PhD student, who have a very good grasp of mathematics and computation mechanics. And so I think that, yeah, the thing open, anyone is interested, I can certainly help them, because I think it's an interesting problem.
It's a fascinating area, as always. Yeah. Thank you, Professor Detournay.
And thank you again for hosting me. I think it was a delight. As I said, I'm very honored to have been invited. And good luck with your seminars. I plan to attend as much as possible. So I'll be there.
Yeah. Thank you very much. Thanks.
Yeah, please do. And hopefully, once the pandemic ends, we'll be able to host you on our campus as well. Thank you. Thank you once again.
That will be your first visit to India, not virtually. Thank you.
Thank you very much. Bye-bye.
Bye-bye. Thank you so
Good
much.
evening.
Yeah.
Good evening. Bye-bye.
Yeah.
Bye.
Have a good day.
Thank you. Bye-bye.
Bye-bye. Yeah.